Hi everyone, in the previous video I showed you how to construct interesting sigma algebras from algebras. This time I want to show you how to construct interesting measures on them. Our starting point is going to be Carath-Theodory's theorem. Again, which I'm going to state without proofs here. It says the following: let A be an algebra on a set omega, and let B be the sigma algebra generated by A. So recall that this is the smallest sigma algebra that contains everything in A. Okay? If we have a mu naught sigma additive measure on A, let me denote it this way, so the set omega and the algebra A, then there is a unique extension of mu naught to omega and the sigma algebra generated by A. Okay, which is a measure, a unique extension as a measure to omega and the sigma algebra generated on A. Okay, so what does it mean to have an extension? Extension means that obviously the sigma algebra generated by A contains all subsets of A, and the extension will have the same value as the original mu naught on A, but the extension will be a measure on all of the sigma algebra generated by A. Okay, so that's the content of this theorem. And then let me show you again a very interesting and important example. Take a distribution function. Let f be a distribution function, probability cumulative distribution function, so obviously this guy will go from R to the interval 0, 1. Okay, it's a cumulative distribution function, so its limit is 0 on the left, 1 on the right, it's non-decreasing, and right continuous. Okay, and then define the sigma additive measure P on intervals of the form AB open on the left and closed on the right by the value of this distribution function at B minus the value of this distribution function at A. Okay? What happened here is that essentially by making this definition, and of course adding the fact that it should be a sigma additive measure on the following algebra, the one we did before, namely the algebra of finite unions of exactly this type of intervals. Okay, it's very easy to extend this definition to a sigma additive measure on this algebra. Namely, if you have disjoint sets of this form, you simply just add up these values of PAB. Okay, so this one is easily a sigma additive measure on the algebra A from before, namely this guy here. Okay, so it's easily extended to a sigma additive measure there. And then what was our next step before? Well, before we said that we want to generate the smallest sigma algebra that contains this one here. Okay, and this is what we call the Borel sigma algebra. According to Carath-Theodory's theorem, this actually extends from A to the sigma algebra generated by A, which we call the Borel sigma algebra on R. Okay, and this is called the Lebesgue-Stieltjes measure. Lebesgue-Stieltjes measure. What is this measure actually measuring? Suppose that you now have a random variable. I haven't told you yet what a random variable is, and it's coming, but just coming back to probability 1, suppose that you have a random variable with this distribution function, then clearly this probability will tell you the probability that your random variable is larger than a strictly and smaller than or equal to b. So this will define you probabilities of intervals for your random variable to be in, and this extends to the Borel sigma algebra. So now you can ask, what is the probability that my random variable is in a set that belongs to the Borel sigma algebra? And it will make sense. The answer will be the Lebesgue-Stieltjes measure of that set. Okay, so let me just expand this a little bit. If B is an element of the Borel sigma algebra on R, it could be an interval, it could be a limit of intervals, it could be a single point, it could be a lot of things, practically anything you can think of almost. Then the Lebesgue-Stieltjes measure of B, denoted by P of B, is just going to be the probability that a random variable is in that set B if the random variable x has f as its cumulative distribution function. Okay, that's just an example, just an intuitive example, because I have not yet defined what a random variable is, and it's coming in a second, but or actually in the next video. But just to have something in mind, the Lebesgue-Stieltjes measure will tell you the probability that x is in some set. Okay, and this is how it's constructed. You take a distribution function, you do this probability on intervals, and then you show that this is sigma additive on A, it's easy, and then this extends by Carath-Theory's theorem to all of the sigma algebra, the Borel sigma algebra on R. As a sub-example, if you wish, if f is of the following form, oops, you don't see the bottom of this. So if f is of the following form, it is just going to be 0 up to some point, say 0, and it's going to be 1 at point 1, and maybe a linear, just the identity function, a linear increase in between. This is 1. Then clearly what I showed here, what I plotted here is just the distribution function of the uniform random variable. Okay, if this is my f, then what I generated by the above construction is that P is just going to be the Lebesgue measure on the interval 0, 1. Okay, because if you take any subintervals here, then it's just assigning the length of that subinterval. If you take probability of AB as above, suppose that A and B belong to this interval 0, 1. So suppose that A is smaller than B, smaller 1 and bigger than 0. Okay, so let's assume this. Then P of AB is just going to be by the definition above FB minus FA. However, on this interval, the function f is just the identity function. On this piece here, f is just identity. So it's b minus a. In other words, we assigned the length of the interval AB with this measure, and that's exactly what the Lebesgue measure does. And this extends to a measure via the above construction, and that's how the Lebesgue measure is constructed. Okay, now if we come back to the previous video, the conclusion of the previous video, I talked about R to the n. This construction here extends to R to the n. So we did the Borel sigma algebra on R. We looked at finite unions of rectangles in R to the n. So we looked at finite unions here, okay, and we managed to construct the Borel sigma algebra on R to the n. Now, in the same way, the whole construction carries over, and we can define the Lebesgue-Stieltjes measure on R to the n. Okay, so we can have measures on the Borel sigma algebra on R to the n, and then those interested can look up Kolmogorov's theorem, which makes a way to define measures on the Borel sigma algebra on R to the infinity. So we can talk about the probabilities that some kind of sequences do something, or even on the Borel sigma algebra of R to a continuous set, so continuous processes like Brownian motions do something. So this is all extended from here further by Kolmogorov's extension theorem. I'm not going to go into the details of that because that goes beyond this unit here.